Friends, as you know, the history of aviation is full of strange aircraft, but the most anomalous project of the 20th century was the revolutionary French interceptor Leduc 0.22. And today, it is the main star of our episode. How did this fantastic machine, with a hollow tube instead of a conventional engine, intend to playfully shatter the sound barrier? Why did this masterpiece of engineering strike fear into its competitors and remain decades ahead of its time? And most importantly, who destroyed the project so suddenly and ruthlessly at the very peak of its triumph? Watch this video to the very last second, and I will reveal the shocking truth about how the buried secrets of the Leduc 0.22 secretly crossed the ocean to give birth to the most legendary black aircraft in US aviation history. Imagine an engine that has nothing unnecessary. No compressor, no turbine, no rotating blades, gears, or bearings. Just air, fuel, and fire. This isn't science fiction. This is a ramjet engine. One of the simplest, and at the same time, one of the most demanding engines ever placed on an aircraft. Let's break down how it works. A conventional jet engine first captures outside air and compresses it using a compressor. A compressor is a system of rotating blades that acts like a pump. Compressed air is mixed with fuel, ignited, and the hot gases blast out the back, pushing the plane forward. Hundreds of moving parts, constant rotation, complex mechanics. A ramjet engine does the same thing, but without a compressor. Instead, it uses the speed of flight itself. When an aircraft flies fast enough, the incoming air packs so tightly into the intake that it compresses on its own, simply due to the shape of the duct. No moving parts. Air enters, compresses, mixes with fuel, ignites, and the jet stream exits the rear. That's it. That's the entire engine. It sounds elegant, and it truly is elegant. But this elegance comes with one harsh condition. The airspeed at the intake must be high from the very start. No speed, the engine simply won't start. At all. Ever. The first person to put this idea on paper was Hungarian engineer Albert Fono. In 1915, he described the concept of a shell with a ramjet engine to increase its range. The idea was noted and then put on a shelf. 20 years passed. Aviation took huge steps forward. Speeds increased. Engineers around the world began to seriously think about the next frontier. And once again, they remembered the ramjet. Simple, powerful, no moving parts, meaning almost nothing to break. But that one problem remained. A ramjet engine works perfectly at high speeds, but it cannot accelerate to those speeds on its own. It needs to be moving fast to even begin to function. Imagine a lighter that provides a flame, but only if you are already holding a lit match. The lighter is beautiful. The lighter works. But without that first match, it's just a piece of metal. For over 30 years, engineers could not solve this task. Most of them eventually pushed it aside and returned to turbojet engines. More complex, heavier, more parts. But they work from zero, from a standstill, with no special conditions. Most of them, but not all. René Leduc was not a theorist. He didn't write articles for scientific journals or give speeches at conferences with pretty diagrams. He was an engineer in the truest sense of the word. A man who took an idea and turned it into metal, bolts, and wires. In 1938, he was 40 years old. Behind him was years of experience in the French aviation industry. Ahead of him was a task most of his colleagues had already abandoned. He decided to build an aircraft with a ramjet engine. Not a missile, not an unmanned drone. An aircraft with a pilot on board. Think for a second what that meant in 1938. No off-the-shelf solutions. No predecessors to learn from. No textbooks with a chapter on how to build a ramjet aircraft. Only theory, a blank sheet of paper, and the starting problem that no one had yet solved. Leduc started with the basics. If the engine can't accelerate itself, it needs help. It needs a carrier, another aircraft to lift the ramjet machine into the air, accelerate to the necessary speed, and only then would the engine start, like a rocket ignited in flight. This solution sounds simple when explained in words. In practice, it meant designing two things at once: the experimental aircraft itself and the entire attachment system under the carrier's fuselage. Docking points, release mechanisms, synchronization. Work went slowly. Funding was modest. Conditions were far from ideal. A few times, it seemed the project would hit a dead end. But Leduc continued. Year after year, he refined the shape of the air intake, recalculated the parameters of the combustion chamber, and solved the question of the pilot's cockpit, which had to be placed so it wouldn't interfere with the airflow entering the engine. Each solution birthed a new list of questions. By 1947, 9 years after he began, the first prototype was ready. 9 years. Now imagine what was happening in aviation around him during that time. In 1944, the German Messerschmitt Me 262 took to the sky, the first mass-produced turbojet fighter. In 1947, American pilot Chuck Yeager broke the sound barrier in the Bell X-1 rocket plane. Turbojet engines were improving every year. The entire aviation world was looking ahead, seeing the future in turbojet machines. At that moment, Leduc finished an aircraft with an engine that most experts considered an interesting but futile idea. Too conditional, too difficult to start, too niche. He was sure they were wrong. And now, he had a way to prove it. When the Leduc 0.10 was first rolled out of the hangar, people stopped and stared. Not because it was beautiful, but because it was unclear what they were actually seeing. Imagine a large metal tube, round in cross-section, pointed at the front, with small wings on the sides and tail fins at the back. The diameter of the tube was about 1 meter. The total length of the aircraft was just over 7 meters. The entire structure was, essentially, the engine. A tube with wings. Air enters the front, passes through the combustion chamber inside, and blasts out the rear. This is a ramjet in its purest form. But wait, if the whole tube is the engine, where does the pilot sit? This is where it gets interesting. The pilot sits in the front, right in the center of the tube, inside the air intake. In a pointed capsule, inserted into the front opening of the engine like a cork in a bottle, only streamlined so the air could flow around it and into the engine. The pilot literally sat inside the engine. Imagine climbing into a metal capsule a little over 0.5 meter in diameter. Surrounding you are the walls of the air intake. Right in front of you is a small porthole. You can look forward. But side visibility is another story. The designers understood the problem. A pilot in such a capsule was essentially blind to the sides, and that is critical in flight. The solution they found was just as unconventional as everything else about the plane. In the walls of the stator, the outer tube of the engine, they installed portholes. Small windows right into the engine's metal. The pilot looked through them and saw the space to the sides, looking through the walls of the tube he was sitting inside. Nowhere else in the world did a pilot look at the sky like that. Now, about safety. The designers understood. If something went wrong at high speed, the pilot needed a chance to survive. You couldn't fit an ejection seat in that capsule. There was nowhere to eject to. You were inside a tube. The solution: the entire nose capsule with the pilot separated from the aircraft as a whole, like a standalone rescue module. The pilot stayed inside, the capsule slowed down and descended. Essentially, it was a rescue capsule, a concept that is still considered advanced in aviation today. In the Leduc 0.10, it was included from the very first blueprint. In 1947, now, about another problem. How to get this aircraft into the air. A ramjet won't start on the ground. It won't start during a slow takeoff roll. It needs speed, right away, from the start. Roughly 200 kilometers per hour or more for the air to properly compress within the intake. Leduc solved this simply and radically. The Leduc 0.10 was attached to the top of the fuselage of a large Sud-Est SE-161 Languedoc transport plane. The Languedoc would take off, reach the necessary speed and altitude, and only then would the Leduc 0.10 detach and begin independent flight. 2 aircraft in one, carrier and missile. One takes the other to the launch point, like a slingshot accelerating a stone to the necessary speed. The system looked cumbersome, but it worked. The morning of April 21st, 1949, Blagnac Airfield, near Toulouse, in the south of France. The Leduc 0.10 was already secured on top of the Sud-Est Languedoc. Below was the wide belly of the carrier. Above, the sharp nose of the small capsule sticking out of the center of the air intake. 2 planes, 1 rig, 1 goal. The pilot took his place in the capsule. The hatch was sealed. Outside, the April sky over Toulouse. Inside the capsule, instruments, control levers, and the smell of metal and hydraulic fluid. A porthole in front, windows in the tube walls to the sides. The entire field of view was just a few small panes of glass in the metal. The Languedoc began its takeoff run. The carrier's 4 piston engines reached full power. The rig accelerated, left the ground, and began to climb. The pilot waited. 1 minute. 2. 5. The plane gained speed and altitude. The instruments in the capsule showed the parameters. Everything was going according to plan. So far, according to plan. And then, the command. The locks released. The Leduc 0.10 separated from the carrier. A split second of silence. That special silence when the machine is already flying on its own, but the engine hasn't started yet. Just the air outside and the beat of your own heart. Then, the pilot opened the fuel supply. The combustion chamber inside the tube, that same tube where the pilot sat in the front, ignited. The ramjet engine roared to life. A jet stream blasted out the back. The aircraft surged forward. 12 minutes. That's how long the engine ran that day, at half power, in a cautious first test mode. Not full throttle, not at the limit, at half. Just to check, does it actually work? During those 12 minutes, the Leduc 0.10 accelerated to 680 kilometers per hour, at half power. The engine was shut down. The pilot performed a planned descent and landing. The ground crew looked at the stopwatches and telemetry data. It works. Everything is working exactly as Leduc calculated. Tests continued. Gradually, the modes became tougher, speeds higher, tasks more complex. And with every new flight, the data became more interesting. During subsequent test flights, the Leduc 0.10 reached a speed of 0.84 Mach. Mach number is the ratio of flight speed to the speed of sound. The speed of sound at cruising altitude is about 1,225 kilometers per hour. 0.84 Mach is roughly 1,030 kilometers per hour. Almost the sound barrier. On a craft conceived 9 years earlier on a blank sheet of paper. But there was another figure. It impressed the specialists even more. Climb rate is how fast an aircraft gains altitude. The higher this indicator, the faster the aircraft gets up. In aviation, this is a key parameter, especially for combat machines. The Leduc 0.10 showed a climb rate of 39.6 meters per second. The best serial jet fighters of the time climbed at a rate of 25 to 30 meters per second. An aircraft without a compressor, without a turbine, without a single rotating part in the engine. Climbing faster than the best combat machines with full-fledged turbojets. Leduc stood at the stand with the data and said nothing. After the success of the Leduc 0.10, the program finally got what it lacked for so long: attention and funding. The French government looked at the test data and saw what Leduc saw: technology with real potential. Not just an interesting experiment, potential. Work on the next model began almost immediately, and from the start, it was clear. This wouldn't just be an improved version of the first plane. This would be a step into another league. The Leduc 0.21 was about 30% larger than its predecessor, but size wasn't the main thing that changed. The main change concerned the pilot. Remember how in the Leduc 0.10, the cockpit was right inside the intake? The pilot sat in the tube, looked at the world through portholes in the engine walls, and hoped the side visibility would be enough. In the Leduc 0.21, they abandoned that solution. The cockpit was moved outside the engine and installed on top, above the intake. A separate canopy. A normal circular view. The pilot finally saw the sky like a pilot of any other aircraft. not through windows in the walls of a tube. This solution improved not only pilot comfort, but also flight safety, because a pilot with a normal view works more accurately, reacts faster, and makes fewer mistakes. The Leduc 0.21 tests yielded results that spoke for themselves. Maximum flight altitude, 20,000 meters. Let's pause at this figure. 20,000 meters is 20 kilometers above sea level. Most airliners today fly at about 10,000 to 12,000 meters. That means the Leduc 0.21 climbed twice as high as a typical airliner. At such an altitude, the sky is no longer blue. It is dark blue, almost black. The horizon curves. The dense layers of the atmosphere are far below. Maximum speed during tests? 900 kilometers per hour. And now, an important figure to understand the context. The speed of sound at cruising altitude is about 1,200 kilometers per hour. This is the boundary aviation calls the sound barrier. It was first broken in 1947 on a special rocket plane launched from a carrier, one that didn't take off on its own and used a rocket engine. The Leduc 0.21 reached 900 kilometers per hour on a ramjet engine. It was 300 kilometers per hour away from the sound barrier, about 25% of the goal. This wasn't just an encouraging result. It was a clear technical signal. The next aircraft, if done right, could cross this boundary. Leduc understood this. His team understood this. The French military aviation program understood this. The only question was, what should the next step be? What did doing it right mean for a machine that had to cross the sound barrier and go beyond? Leduc had the answer. And that answer required a solution that turned the very logic of aircraft design upside down. 900 kilometers per hour, 20 kilometers altitude. The next aircraft had to double the speed and make the ramjet self-sufficient, no longer needing a carrier. Leduc sat down at the drafting board. The Leduc 0.22 didn't look like its predecessors. If the Leduc 0.10 was a tube with wings, a craft that resembled a missile more than an airplane, the Leduc 0.22 was a real combat machine. Sharp nose, swept back wings at a sharp angle, length about 17 meters. The cockpit was now where it was supposed to be, in the nose, on top, with a normal canopy and normal visibility. From the outside, it resembled what they called the plane of the future in the mid-50s. Inside, everything was arranged quite differently from any other aircraft of the time. Let's break down the design step by step. The basis of the Leduc 0.22 was still that same annular ramjet engine. A large air intake at the front captures air, compresses it with the shape of the duct, mixes it with fuel, and blasts it out the rear as a jet stream. The same principle as the Leduc 0.10, the same logic, the same elegance. But now, this engine had to accelerate the plane to Mach 2, twice the speed of sound. Mach 2 at cruising altitude is roughly 2,470 kilometers per hour. For comparison, the cruising speed of a modern airliner is about 900 kilometers per hour. The Leduc 0.22 was supposed to fly almost 3 times faster than a passenger plane. But here, that same problem arose again. A ramjet doesn't work at low speed. That means the plane can't take off on its own. That means it needs a carrier. Another 2 planes. Another complex attachment and release system. This limitation was what prevented the program from moving beyond a pure experiment. An interceptor that needs a carrier is not an interceptor. It's a lab sample. Leduc decided to get rid of the carrier once and for all. The solution? Inside the annular ramjet, right in the center of the tube, install a second, separate engine, a turbojet. Small, but powerful enough for takeoff and acceleration. In the Leduc 0.22, this turbojet was the Turbomeca Marbour, a French engine that was already used on trainers and had proven itself well. Compact, reliable, proven. Here is how it worked in practice. During takeoff and acceleration, only the Turbomeca Marbour, the turbojet in the center of the tube, runs. The plane accelerates in the usual way. When the speed reaches the value where the ramjet can work properly, fuel is injected into the annular combustion chamber of the ramjet circuit. Both engines run simultaneously. Thrust increases sharply. The plane accelerates further. At high cruising speeds, the main thrust is provided by the ramjet, the large annular one running at full power. The turbojet at this moment either continues to run at low thrust, or its role becomes auxiliary. Imagine two runners. One is a sprinter, fast at the start but lacking endurance over long distances. The other is a stayer who needs time to accelerate but can go far and fast. You put them in one harness. The sprinter does the start. The stayer takes the distance. That is exactly how the Leduc 0.22 propulsion system worked. Two different principles in one body. Each does its job. Neither interferes with the other. The plane takes off on its own, accelerates on its own, reaches cruising mode on its own. No carrier needed. This wasn't just technical progress. It was a change in concept. The Leduc 0.22 was no longer an experimental craft. It was becoming the foundation for a real combat interceptor. On December 26, 1956, the Leduc 0.22 flew on its own for the first time. Think about it. 19 years had passed since Leduc began working on the ramjet aircraft in 1938. 19 years of calculations, blueprints, tests, redesigns, and compromises. And here it was, an aircraft with a ramjet engine taking off on its own, without a carrier, from a regular runway. It was a personal triumph for René Leduc. Test flights continued. Data was accumulated. The machine behaved exactly as predicted on paper. Everything pointed to the program being on the final stretch. And the Mach 2 goal was now a matter of time and further testing, not possibility. No one at that moment knew that time was almost up. The Leduc 0.22 was flying. Data was being accumulated. The program was moving forward. And at that exact moment, everything stopped. Not because of an accident, not because of a technical problem, not because the aircraft didn't live up to expectations. The program was closed for one reason. The money ran out before the tests did. But to understand why this happened right then, you need to understand what was going on around Leduc's program in the late 50s. The aviation world was changing rapidly. On one hand, missiles. After the Soviet Union launched the first artificial satellite in October 1957, strategic thinking around the world took a sharp turn. If a rocket can put an object into orbit, it can deliver anything, anywhere, faster than any plane, higher than any interceptor. Many military theorists at the time concluded that the era of manned interceptors was ending. The future belonged to guided missiles. Why build a complex aircraft with a pilot if a missile does the same job faster and cheaper? That conclusion would prove premature. History would show that in the next decade. But in 1958, it seemed obvious to many people making funding decisions. On the other hand, competition within the French aviation industry. While Leduc worked on his ramjet machines, another French company, Dassault, was developing its own jet fighter. The plane was called the Mirage 3. Delta wing, conventional turbojet engine, capable of speeds over Mach 2. The Mirage 3 took off from a regular runway. It didn't need a special launch system. It didn't require a separate carrier, even though by that time, the Leduc 0.22 had solved that problem on its own. It was understood by the military from an operational standpoint, and it showed excellent results. The French government looked at the two planes standing side by side on the airfield. One, revolutionary, with a fundamentally new propulsion system, needing more time and money to bring to combat standard. The second, more traditional in design, but ready for serial production much sooner and much cheaper. With a limited budget, the choice was made in favor of the Mirage. Leduc's program lost its funding. Think about what that meant in practice. The Leduc 0.22 had performed independent takeoffs. It flew. It collected data. It was on the final stretch toward the Mach 2 target. A final stage of testing, gradually reaching maximum modes, which required time and a few dozen more flights. It wasn't a failure. It wasn't a dead end. It was the home stretch before the finish line. And that is where they stopped the program. René Leduc was 60 years old in 1958. He had spent 20 years working on one idea. 3 aircraft, hundreds of test flights, dozens of technical solutions, each designed from scratch because no textbooks existed. He didn't leave behind any widely known public statements about the program's closure. But imagine yourself in his shoes. 20 years, 3 planes, and a signature on a piece of paper that said, "Enough." What happened to the planes? The Leduc 0.10, the first prototype, the one that launched the engine in the air for the first time on April 21, 1949, survived. Today, it is in the Air and Space Museum at Le Bourget, near Paris. If you are ever in Paris and want to see this plane in person, it's there. Small, sharp, strange. A tube with wings that once outperformed the best fighters of its time. The Leduc 0.22, the last and most ambitious of the 3, did not survive to this day. The program was closed, funding was cut, blueprints were put in folders. René Leduc returned to private engineering practice and continued working on various technical projects until the end of his life in 1968. Officially, the story ends there. But that is not the whole story. Because the ideas Leduc wrote down in those folders didn't just stay on a shelf. They found those who needed them. And what was built based on them still flies in aviation museums around the world as a symbol of another era. An era when the fastest plane in history was still just a dream. While Leduc's program was closing in France, something important was happening on the other side of the Atlantic. In the late 50s, the U.S. Aerospace Agency and the Air Force gave Lockheed a task that at first seemed impossible. They needed a reconnaissance aircraft, but not a normal one. It had to fly so high and so fast that no anti-aircraft missile or interceptor in the world could catch it. Not because it was armed and could defend itself, but because its speed and altitude made interception physically impossible. The task was given to Lockheed's secret unit, the Skunk Works. By then, this unit already had a reputation for doing the impossible on tight deadlines. It was led by engineer Clarence Kelly Johnson, a man his colleagues said saw the solution before others could even formulate the problem. Johnson and his team began designing, and almost immediately they encountered the same fundamental problem René Leduc had been solving for 20 years before them. If a plane needs to fly at speeds over Mach 3, that's over 3,000 kilometers per hour at cruising altitude, a conventional turbojet doesn't work efficiently. Its compressor and turbine create drag, lose power, and disintegrate from the monstrous heat. At speeds above Mach 2.5 to 3, a conventional turbine becomes not a helper, but an obstacle. But a pure ramjet won't take off from a runway. They needed something in between, something hybrid. This is where Lockheed's engineers arrived at the same conclusion Leduc had reached a few years earlier. The engine for the new aircraft, designated the Pratt & Whitney J58, was built on a principle that could be called a controlled transition between 2 operating modes. During takeoff and acceleration to medium speeds, the J58 runs like a conventional turbojet with an afterburner. The compressor compresses the air, fuel burns in the chamber, gases escape through the turbine and afterburner. Everything is familiar. The plane takes off, accelerates, and heads into the stratosphere. But then, different physics kicks in. When the speed reaches about Mach 2.2, special bypass ducts open in the engine. Some of the air from the compressor starts to go not through the turbine, but directly into the afterburner. The higher the speed, the more air bypasses the turbine, and the more the engine begins to operate on the ramjet principle. At maximum cruising speed, over Mach 3, up to 80% of the J58's thrust is created precisely by the ramjet circuit, not by the turbine, not by the compressor, by the speed and the shape of the air intake. 2 modes, 1 engine, turbojet at the start, ramjet at cruise. This is not a coincidental overlap with the Leduc 0.22 idea. It is the same engineering logic, written down by other people in another country a few years after the French program was closed. And there was one more element. Anyone who saw the Leduc 0.10 will immediately understand what I'm talking about. The air intake of the SR-71 Blackbird. At the front of each of the 2 Blackbird engines stands a conical center body, a sharp cone that breaks the incoming airflow and forces it to compress before entering the engine. The SR-71 pilot, looking forward from the cockpit, saw two such cones, one in front of each engine. The Leduc 0.10 pilot, sitting in his capsule inside the air intake, looked at the sky through that same principle, only from the inside. The shape is different, the scale is different, the era is different, the physics is the same. On December 22, 1964, the SR-71 Blackbird made its first flight. From 1966 to 1998, it served in the U.S. Air Force. Throughout its service life, not a single SR-71 was shot down by an enemy, despite more than 1,000 anti-aircraft missiles being fired at it. Every time, it simply accelerated and flew away. The officially recorded maximum speed is 3,529 kilometers per hour. That is more than 3 times the speed of sound. This record for air-breathing jet aircraft has not been broken to this day. Think about it. The fastest jet aircraft in human history, a machine that no one has surpassed in speed yet. And at the heart of its propulsion system lies the very idea that a French engineer began developing in 1938 in Toulouse. René Leduc lived until 1968. He lived to see the SR-71 Blackbird enter service. He lived to see the world recognize the practicality of what he was the first to prove. He lived to see that he was right. He just happened to be right in the wrong country and at the wrong time. It's unfair. And at the same time, it's perfectly normal for the history of major technology. Ideas rarely belong to the one who wrote them down first. They belong to those who found the right moment for them. Leduc found the idea. He proved it worked. He solved every fundamental problem, one after another, over 20 years, on 3 successive aircraft. Carrier no longer needed? Solved. Leduc 0.22. Pilot can't see? Solved. Leduc 0.21. Ramjet engine won't start? Solved. Leduc 0.10. April 21st, 1949, 12 minutes over Toulouse. He did everything one person could possibly do. If you are ever in Paris, get to the Air and Space Museum at Le Bourget. There, among the big, beautiful planes, stands a small metal tube with wings. Sharp nose, portholes in the engine walls, 7 meters long. This is the Leduc 0.10. Stand next to it. Look at those portholes on the side of the tube. Think of the man who decided that a pilot could sit inside an engine and look at the sky through a hole in the metal. And then remember the black silhouette of the SR-71 Blackbird heading into the stratosphere at a speed no one has repeated. These two machines are separated by 15 years and 2 continents, but the same heart beats within them. Thanks for watching, and see you next time.